In this video, we're going to look at angles as they relate to circles, both inside and outside of a circle. We'll start with this first property. Inscribed angles subtended by the same arc are equal. So what do we mean by this word subtended? Well, the word subtended really just means that the angle, the inside angle, angle inside, that makes up this, when it says subtended by the same arc. So this angle is made up from this arc. So the arc kind of gives us the endpoints, or at the opposite end of the angle. So inscribed angles, so that means that they're in a circle, subtended by the same arc are equal. So here's an angle right here. I'll call it x for now. An angle x that's subtended by the arc AB. And what this property says is that we can draw any number of any number of angles subtended by that same arc. So what I mean by that is, let's create an angle that again goes from A to the circumference of the circle and then back to B. So here's another angle that is subtended by this arc AB. So it's subtended by this arc. These are two angles that are subtended by the same arc, and any two angles that are subtended by the same arc are equal. So that means that this angle up in here also has to be x. So that's an example there. Sometimes people call this the bow tie theorem. It kind of looks like a bow tie, just showing you that the angles are the same. So that's a simple version of it. You might see it that looks kind of more like this, maybe a little bit sort of more polished, I guess, showing that x and y are two angles that are actually the same. So that's a nice way to see it. This next one here talks about the central angle. So the central angle is the angle that goes to the center of the circle. And it says here that the central angle is twice any inscribed angle subtended by the same arc. So again, here's that arc. Let me maybe just highlight the arc. Here's that arc AB. And this is the inscribed angle. So it's inside the circle, and it's subtended by this arc AB. So the end of that angle is this arc AB. And what the first part says is that the central angle, so the central angle subtended by the same arc. So we're going to draw an angle that goes from the endpoints of that arc, so from A to B. And what this theorem says is that the central angle is twice the angle, the inscribed angle. So here's the inscribed angle. We'll call this x. We can call it whatever we want, but we'll call it x for now. And if this angle here is x, that's the inscribed angle, then the central angle has to be 2x, has to be 2 times that. So if we know that well, let's try that again. If we know that inscribed angle is 30 degrees, then we know that this central angle has to be twice that, which is equal to 60 degrees. All right, and then we'll move on to this last one on this page. And it says that any angle subtended by a diameter is always 90 degrees. This is actually just a special case of this version here that we looked at. So here we have, if you want to, we can look at it this way. Call this A and call this B. There's our central angle, and so maybe just get a straight line here. There we go. So again, we're still going from A to B. The central angle here is 180 degrees. So using this property up here, the angle in here must be half of that, must be 90 degrees. So what this property says, let's see if I can kind of draw this. Oh, I didn't do a very good job. That angle is 90 degrees. So we would show that here. And that's true no matter where we draw the triangle inside the semicircle from this diameter. So I drew it there. Let's maybe draw another one just so you can see what that looks like. So again, going from A to B, or I guess A to the edge of the circle, and then to B, that angle in there would be 90 degrees. It can actually, this is one of those things that if you do a little bit of artwork, can look kind of interesting, right? If we continue to draw these triangles all the way around the edge of the circle, we kind of get some interesting looking patterns. So anytime we draw a diameter and draw a triangle inscribed in the circle, going from each end of the diameter to the circumference of the circle, we get a 90-degree angle. Again, that's just a special version of this second property that we looked at. All right, let's move on. There are a number of other properties that we're going to look at here, dealing specifically with chords and tangents. So a radius in a circle that is perpendicular to a chord. So here's the radius going from the center of the circle to the edge. And if it's perpendicular to a chord, so remember a chord is just a line that connects 2 points on a circle. So if we're perpendicular to that chord, then that radius, or it could be a diameter as well, is going to bisect the chord, meaning it's going to be cut exactly in half. This length here and this length here will be exactly the same length. So again, if a radius is perpendicular, maybe I should draw that in, that this is perpendicular. That's the important part of this. So the radius, that looks more like a semicircle than a 90-degree angle. Let's try that again. So again, if that radius or diameter is perpendicular to the chord, then the chord gets cut in half. All right, the next one here is about a tangent. So just a reminder, a tangent is a line that just touches the edge of a circle. We can see here that we get a tangent. It just touches the circle at point P. And this one says that a tangent to a circle is perpendicular to a radius drawn at the point of tangency. Tangency? So here's our point P, our point of tangency. And if we draw a radius from there to the center of the circle, that's going to form a 90-degree angle. So again, I can draw in that 90-degree mark, which is a very useful property for those of you that go on and study more math. Oh, let's try that one more time. That looks horrible. All right, that's a little bit better. So again, we get that 90-degree angle. All right, and the last one on this page dealing with tangents has to do with two line segments outside a circle if both of those line segments are tangent. So we look at this line segment AC here. I'll highlight that. So that's a tangent that runs from some point to the circle, and we have another tangent that runs from the same point to the circle. A couple things are going to happen here. Basically, these two segments are going to be equal in length. So you can see that by this line here indicated. So those two parts are going to be the same. You can see now that we actually have two triangles that are similar triangles. Again, from the previous property, this point of tangency and the radius are going to form a 90-degree angle. These are both radii, and we've got 90-degree angles. We've got similar triangles here. Obviously, the length from here to here is the same, and the other angles are also equal. So that's an interesting property there. All right, let's move on. We've got a couple more to cover, and then we'll do a couple of examples. Oh, sorry, just one. I thought there were two, but just one. All right, chords of the same length, either in a circle or in a circle that has the same diameter or same size, produce arcs that are the same length. So if I create a chord here, if I have a chord here in the circle, and that chord is the same length as this chord, then the arc lengths here and here are also going to be the same length. And it doesn't matter where I draw that chord. I drew these ones kind of in the same direction, but if I took a different chord that was exactly the same length, that's the key here, is that they have to be the same length. If I took a different chord that was the same length and drew it kind of going this direction, then this arc length would also be the same. But again, the key is that the chord has to be the same length. That one I didn't check, so I'm just going to get rid of it. All right, let's put some of this to use. We'll look at a couple of examples here about how we can use this information to find missing values. And on a later date or later video, we'll work through some sort of examples where you might see this come up. But for today, we're just going to try to work on the basics here. All right, so here we have two angles in a triangle. I think we're going to pause for a second. Sorry about that, I had the wrong image there. So here we are with this image. So we have two angles here. We're trying to find angle Y. A quick note here is that we have, just grab a highlighter here. We have this arc here subtended by this angle here of 40 degrees. So we have that arc subtended by that angle of 40 degrees, or the angle subtended by the arc. And then we have similar situation happening right over here. So here's the arc again, and we have this angle here. So these are two angles subtended by the same arc. So these two angles have to be equal. And so in this case, we could just say that y is equal to 40 degrees. Let's try that again. Y is equal to 40. And we should maybe give a rationale why this is true. Sorry, I'm having a hard time. And our rationale here could be just that the angles, I'll just type this, be a little bit faster. Angles subtended by the same arc. And that could be our rationale. So that one wasn't too hard. It was just recognizing that pattern. Again, sometimes people call that the bow tie pattern. So if you recognize that pretty quickly, you can go from there. All right, let's try this next one here. Maybe we'll give these some titles so we can kind of refer to them. We'll call this example A. And the next one we can call example B. And in this case, we have a diameter. So we have a diameter over here. And from there, we've got a triangle that goes out to the circumference of the circle and back to this other point here on the circle. And so this is a situation where we have this triangle that's inscribed in the circle using a diameter, and that means that this angle here is going to be 90 degrees. So this is a 90-degree triangle, right angle triangle. And if we have a right angle triangle, we should be able to use the Pythagorean theorem to find the missing value. I'm just going to label my triangle here just so we're all on the same page here. This is the hypotenuse. And the other two sides, oh, sorry about that. The other two sides don't really make a difference, but our two legs of our triangle are the 12 and the x. So just a reminder with the Pythagorean theorem, there are lots of ways to refer to it. I use this one, but if you use a different version, that's fine too. C squared is equal to a squared plus b squared, where this c squared is always equal to the hypotenuse. So we've got 13 squared is equal to 12 squared plus x squared. I think I need to adjust my pen again. $13 squared is 169. That's equal to 12 squared, which is 144. Plus x squared. We want to solve this equation. So subtract 144 from both sides. And 169 minus 44. I guess I should write that down so we can see what we did here. That's equal to y squared. Y squared is equal to 25, which means that y is equal to 5. And so here we get an answer of y equals 25. Sorry, y equals 5, square root of 25, which is 5. So we just found the missing side length here in this triangle. And we were able to do that because we knew that this was a right angle. Again, the question didn't show that was a right angle, so you might be wondering, why is this not like a grade 9 type of problem? And the answer is that it didn't tell you that that was a 90-degree angle. We can do the same sort of thing, by the way, using trigonometry. So we'll just kind of quickly go through this example C here so you can see what that looks like. So example C would be the same idea. We've got a triangle in a circle. We've got this diameter here that means that this angle here has to be 90 degrees. And now this is a 90-degree angle. We need to find this angle down here. We can use some right angle trigonometry to do that. So let's just label our triangle. Here's the angle that we're interested in. The opposite side would be this side. The adjacent side would be over here. And the hypotenuse would be over here. So we have the, we have the hypotenuse and we have the adjacent side. So the trig ratio that uses adjacent and hypotenuse would be cos. So we know that the cos of x is going to equal the adjacent side, which is 12, divided by the hypotenuse, which is 13. Now, if we want to find out what x is, we're going to undo cos. We want to get rid of this cos on both sides, so we're going to do the inverse cos to both sides. Doing the inverse cos on the left side will leave us with just y, and then here we'll get the inverse cos of 12 over 13. Again, make sure your calculator is in degrees. We're doing our work here in degrees, so just keep your calculator in degrees. And when you do that on your calculator, hopefully you get an answer that looks like this. We'll just type it in here and see what happens. We're 12 over 13, and I get an answer of 22.6 degrees. So that's how we can find an angle in a triangle that's in a circle. Again, the difference here, just adding on to what you already know about trigonometry, is just identifying that this was in fact a 90-degree angle. In previous courses about trigonometry, we would have told you that that angle is 90 degrees. Here we're not telling you. You have to actually go ahead and find it. All right, let's work through a couple more examples. So these ones deal with the tangent properties, the properties of tangents. So here, and I didn't write this down, I probably should have, but we're going to talk about this x being a tangent. So that's a tangent to this circle that has a radius of 10, and we've got this distance that runs from here to here, which is 10 centimeters. So find the length of that tangent indicated. So in this case, again, it's a right triangle because according to the properties, if we draw a tangent and we draw a radius at that tangent, at that point of tangency, we get a right angle triangle. So again, using the Pythagorean Theorem, we should be able to find x. The hypotenuse is 10, so we know that 10 squared is going to equal 6 squared plus x squared. So that's 100. I'm having some real troubles with my pen, I apologize. Equals 36 plus x squared. We'll try that again. Subtract 36 from both sides, and we get a 64 here is equal to x squared. Take the square root of both sides, and we get x equals 8. So here's an example where we're using some of the properties of the circles and relating it to the trigonometry that you already know. And the last example that we're going to do here looks at a point out here. Call it A, I guess. And two tangents. Again, I didn't say so in the problem, but these two lines here are both tangents to the circle. And we need to find this x value here. So we know that both of these lines have to be the same length because of that property, the two tangents property that we looked at. So if both of these lines are the same length, then 2x plus 3 has to equal 11, and we can just solve that equation. 2x plus 3 equals 11. We'll subtract 3 from both sides. So we get 2x. Oh, here, let me show that. Sorry. So I'm just going to show that in, let's do that in red. Subtract 3 from the left. Subtract 3 from the right. And then that will leave us with 2x is equal to 8. And then we can divide both sides by 2. We get x equals 4. So there were a lot of properties there. We covered some of those properties with some of the examples, but a lot of the other properties can be used in similar sorts of ways. So you'll have a chance to practice using these properties and hopefully doing a little bit of problem solving. As I said, we'll get into some practical kind of problem solving over the next couple of days as well.